شيء تعبان زي هذا.
بس ما
I do, but I forget the name. Yes, and you said you were gonna come. The thing is, I come with like one guy.
you were
I was contact.
قد جربت في هذه الانجكشن
جربتها في Canada was just one.
But again, all of you
I
are
just
just
dropped off.
literally
Actually, the wrong week, the same day. I went to London, yeah. Where you
in other words لانه
Ali?
Yeah. ايوه ايوه
بسم الله. يلا يا جماعة.
Quick introduction.
Yeah.
Alright, so Bismillah. Thank you all for coming. Inshallah, today we're gonna have a lecture about the basics of AI, down to the fundamental cores. And our brother Yasser gave a talk a long time ago here. This wasn't recorded. This is the first time
Yes.
we recorded.
Yeah.
So inshallah, this is gonna be a great one.
Inshallah.
If you want to learn about the fundamentals of AI,
Exactly.
you have to start
Thank
from
you.
the basics.
Exactly.
Machine learning. So
Inshallah.
take it away, Yasser. Bismillah.
يلا السلام عليكم. Everybody, thank you so much for coming. Today I'm gonna discuss about machine learning from data to decision. The idea is, you guys, I know many of us here, maybe they are expert in AI and machine learning. The whole purpose is to start from the basic and then continue. Inshallah, the idea is maybe this is a startup and then we can continue to making like sessions, making workshop, inshallah. Introduction about myself, Yasser Al-Rayah. I'm a data scientist. Been working different companies, including AT&T. Been working at GM, General Motors for a while. I started as a geospatial analytics and then moved slowly into data science. And now working at Domino's headquarters as a data scientist. And I've been doing many of machine learning as well as geospatial analytics at the same time. And I was lucky to work with different algorithms and even created like models and building applications. Right now, there are certain application is running. I will demo at the end of the session one of the applications that I developed and running right now. I don't have the data, but I was able, using AI, generative AI, to at least get some visualization and some concept of the application itself. So let's deep dive. As we all know, machine learning is a subset of AI, right? So we have the bigger picture is artificial intelligence, where we have including like different categories, and under that is machine learning. And of course, the new subset is generative AI. So generative AI is the latest technology that's come under machine learning. And with machine learning, there are many concepts, and it's a huge, it's a jungle of information that you cannot grasp everything, and every day is evolving and learning. So it started with AI, rule-based system, search algorithm, planning tools, and then we have like machine learning in terms of application like Netflix, credit scoring, fraud detection, and then Gen AI, ChatGPT, AI image generator, and video synthetic. There is a new concept, it's called artificial general intelligence, the AGI, and now this is the future, which is an AI not fed by information or by data, but also reason and come up into reasoning and come up into decide what the action that should be. So it's more general, and this is right now, people are working on it. I will mention DeepMind, part of Google. They started as Gen AI and they try to evolve. They have this project. DeepMind is, focused on many things, and including the artificial general intelligence. I'll give you some example of how we use machine learning and AI. For example, and this is just to try, get your insight, like how we translate the theory into application. So this application is actually counting people who are getting into like a store using image processing, and like how people like in and out. So this is one of the application of machine learning where you are able to understand like how many people coming out. I remember one use case is counting sheep in field, like like all those cattle coming in, how many sheep in and out. So translate that like image into classification and into model. That's one of the examples. Another example into gaming, for example. So if you look at this example, this is an example of enforcement learning, where you try to the agent, we call it agent, try to understand and learn by itself, right? By getting reward, by taking penalizing the agent. So here what try to do is like one agent is trying to fight another one, and the other one is trying to learn how to like run away. And by time, like if you look like hour 12, he was successful. He learned how to run away successfully. So this is another example. The most important example in manufacturing, like understanding what objects coming in, how to clean like data out of our objects. So not only identify what the object is, but also classify the object, right? Like for example, is it like a hot bomb or a cold bomb, and then you can take that out. So this is type of examples that could you can translate the theoretical behind the AI and machine learning into a real world application. And of course, at GM, we used to have like, manufacture of car, they use machine robotics. Those machine robotics use AI and machine learning to classify certain objects and, maybe building the car, for example. So this is overview of some of the application of machine learning. But going into basics, what is machine learning? Machine learning, previously in traditional programming, we used to have rules, right? We used to have data, and someone write a program, and based on that, you get an answer, right? We have rules, data, and then your computer program or logic, and you get an answer for that. But machine learning is actually kind of twisted. Is the system, the AI system learn from data to make decisions. So first we give data, we provide data, and then we give examples like answers, how this data will tell us, and then the computer actually using the data and the examples or the answer that we have, it will come with the rules. We are not building the rules. It's the data and the examples will generate the rules. And this is like a high-level concept of machine learning. And of course, rules, it is not like, we need some assistance, and I'm going to explain more like how those rules would evolve or manifest. So the 4 pillars of machine learning, we have supervised machine learning, which is learning from labeled or examples to predict the future. And usually machine learning is about prediction, right? We need to predict the future. And what is the difference between machine learning and the statistical learning? Statistical learning actually we understand the phenomena, right? And then try to come up with a model based on the phenomena, right? Remember linear regression, we have data and we come up with a align, right? So we know we need to come up with a model. But for machine learning, we need to predict, come up with the logic, and we need to predict what the model look like, and we come up with a model and then use that model to predict the future. So always the difference between statistical learning and machine learning is this for prediction for application, and this is for understanding the phenomena. So as I said, we have 4 pillars. And please, if you have any question, yeah, you can always jump in. Supervised machine learning, supervised learning, unsupervised learning. And supervised learning, as I mentioned, needs labeled data. We need some examples so as in the data, embedding the data, so as we can predict it, use it to predict the future. The unsupervised learning is actually finding hidden structure in unlabeled data. So we don't have examples. It just gives you like some data, and you know to understand like those components together. There's also semi-supervised learning, and this is actually both. You have a small amount of labeled data, but also we have a massive amount of unlabeled data, and we need to, using both, come up with a model and then use that model to predict. And of course, and there's a lot of work into this, which is the reinforcement learning. And this is usually through the trial and error and agents that learn by itself. You put an agent into an environment, and then it asks the agent to do something, and depends on its behavior, you either give reward or penalize it, and then it learns by time. And this is like happening right now in automotive industry, in here driverless car or autonomous vehicle, is try to understand the route by itself, right? And there's a lot of research in this area.
When you say label, what does label mean? Labeled data.
Good question. Labeled data means, for example, I have, let's say, a fruit. Okay, so I know this is apple, this is mango. So it's naming those features, right? So I give like a bunch of fruit, and I tell the machine, okay, this is apple, this is orange, as a training example. And then based on that learning, he will, if I give him another fruit, he will tell us what is apple, what is an orange, knowing what is the characteristic of those fruits, for example. And I can explain more into this. This is, as I mentioned, is a subset of machine learning. So AI is the big umbrella. Come under it is machine learning, and then you have like NLP, deep learning. NLP mainly is coming from ChatGPT. ChatGPT is based on natural language processing, right? Text sentiment analysis, natural language processing is coming from that, and that's where chatbot and ChatGPT and the transformer came from. It is not. It is part. It's part of it, but under the generative AI.
I think
Probably unsupervised learning, right? Yeah. Yeah.
And some reinforcement learning, actually, a lot.
Yeah. Question?
I'm stuck between the green and the pink, which is the semi-supervised and the unsupervised.
Yeah, the semi-supervised is I provide you with both. I provide you with labeled data, an item that I know what is it, an apple and orange, and then another fruit, yeah, which is I don't know. It will try to use this one and maybe group those one later on, depends on how you structure the information.
Large language models do that too in training. Actually.
Exactly, yes.
All three,
yes, unsupervised, yeah, semi-supervised, probably semi-supervised. Yes, that's correct, yeah.
I get the green picture if you give it like a clementine, it's a Fendi, and then it's closer to an orange.
Yeah.
But I don't get the pink.
The pink, okay, this answer, I'm going to explain more each one. Okay. So unsupervised learning, so I will give you like just hint right now, is I have, yes, right. So it is like I give you some item, feature, right? And the way the machine need to look at the feature, understand at each one characteristic, and then group them together, right? Maybe feature that is high in value, I put them into high value feature versus small value, put them into small. So group them is unsupervised learning. Does that make sense? So when you group, that's where you will cluster or grouping, that's unsupervised learning. And that's why you see it was like cluster of points, and then you have groups of points together. So the supervised machine learning, as I mentioned, relies on non-answer. So for example, I have here maybe if we try to predict the house price, right? So maybe I give you the size and location, right, as in a feature, and put that, and I give you, for example, a house price. You know, those are bigger house, cost this amount of money, this is cost this certain amount of money. And then based on those two items, the independent variable feature and the non-target and label, or the output, non-output, I will come with a model. It's called trained model, right? And then use that model to predict, data, right? Use it for prediction. So this is like a high-level model of how supervised machine learning happens, or how we come up. The main supervised machine learning divided into two, which is regression and classification. Regression is when we are trying to look at numerical values, like what is the highest, the price of the house, right? What is the age of a visitor, or how, like a number. So we're looking at regression, right? If we try to classify, I have a feature, I need to know what is it, like red or blue or orange or apple or cat or dog, then classify, that's classification. So it's predict a distinct category. We're looking for category class, classification, we're looking for a number or continuous number of value, is regression. So as I mentioned here, forecasting an exact price is a regression. Filtering incoming emails into spam or not spam. You see here at Google, right? You see sometimes you have categories like spam folder, social folder. Those all coming from classification. You see, that's real. So it knows the email based on the structure of the email and based on a previous labels, spam versus not spam. We know, the system knows whether the email is actually spam or not spam, or social media versus not social media, whatever category over there. Okay? So this is how it works, the machine learning. So allow computer to learn task data from data. So first we come up with a data, right? Inputs and outputs. I have like inputs, we call them labels data, we call them features. And then we have an output or outcome, expected outcome, right? This is my training data set, okay? And then I put into learning algorithm. And here we're gonna speak a little bit about learning algorithm. And then I come up with a model. I'm gonna tell you what is the model itself in a minute. So that's phase one. Always phase one is training. Phase two is use that model, the machine learning model, and use it with the new data, okay, to predict. Right? So now I have a machine learning model. I can use it for new data to get a prediction with the new data. So let's look at the phase two.
Question.
Yeah.
The model that's produced, before you actually use it in inference, is it validated?
Of course, that's part of the training. You have to validate it. Here, this is the validation. So of course, the training phase is including validation. So I'm giving you high levels, right? So you train it, and then you validate it, and you get an accuracy. Is it like how accurate is the model? And then use it, right, for prediction. Correct.
Now, when you say the output, you have to have the output.
Of course, yeah, that's what I said, yeah.
With the input. So
Of course, yeah.
You
That's
cannot use the input only.
unless it is unsupervised machine learning. Unsupervised machine and labeled data. So we have only input data. For supervised machine learning, we have input and output, training data set. Okay? And so we have the model. So let's talk about the model itself, right? So I have the machine learning model, which is the inference part. So let's talk about phase two, the inference part. The inference part is I have a model. Like I give you like an example. Y equal mx plus b, right? So this is a model, right? Those are the parameters, b and mx. That came from the model, right? This is the learning algorithm. Learning algorithm is a linear relationship. It may not be a linear relationship, right? So this is a learning algorithm. We are always looking at what? At the parameters. Looking at the parameters. So the learning algorithm is different than the parameters. And here we have the input, we have the prediction, right?
I'm sorry.
Yeah.
I have seen this as A plus BX.
Mm-hmm.
It's the same format.
So
You'd like to put the
it could be anything. It could be an equation. Yeah. Don't hang up with the equation itself. Consider this an equation, right? Whether it's a linear equation, non-linear equation, it has x variables. Uh-huh.
In the 8th grade, your 8th grade kids are looking at mx plus b. Your 12th grade kids are rearranging it b plus ax.
Yeah, it doesn't matter. I don't look at it.
Tells the children.
Right. I mean, yeah. For this context, I'm just give you a function, f of x, right? F of x has a, b, c, whatever parameters. Consider it as that, okay? So we are in training. We are looking for those parameters, for a, b, and x. How we do that? We provide the input data and prediction. The machine will come up with what? With those parameters. Does that make sense? So we have the, and then after we come with our model, the y hat is actually our prediction, and this will predict for tomorrow, like the temperature for tomorrow, and those are the input data, right? So in order to come with this model, I have to have input and output, right? But then I come with a model and use that to predict for the future. Okay? So this is the inference part. But how about the training part? The training part is actually, that's how it works. So I have a set of actual value of y and have an actual value of input, right? It shouldn't be like one, maybe different, a size, right? And then what we do is, or what the machine does, is it will subtract the actual from the predicted with the parameter, and then need to come up with the suitable parameter that can generate a loss function, which is to minimize that loss function. So we call this loss function. It depends on m and b, right? And those parameters. This is optimization. Those parameters that help make the difference between actual and prediction as small as possible, that's where we have the accurate or the most closely accurate model. Does that make sense? So this is the training phase. Yeah.
So meaning if we have a lot of parameters that may also help in reducing the loss factor.
Exactly, yeah. Okay. Yes. So that's why we try to come up with new features. We have let's say we have a set of features. Sometimes we need to add more features to help improve our model. And sometimes we don't need a lot of features. We need to maybe reduce the feature. Every problem has its own. Sometimes you need to use something called principal component analysis to reduce the feature to make it easy for us as an expert to interpret the result. You know what I mean? It's balance between having a large feature and a small feature. Yeah.
You mean features means X?
I mean yes, feature, attributes, feature. Those. That's X. Yep. Correct. Yeah.
The M and the B, where are they coming from?
This is from the machine.
So the
The machine will tell us. Yes. Yeah. Yes. Different values. Yeah. Yes.
And then seeing
Yes.
gives me the best
Exactly. Yes. Yeah. But we have different algorithm. We have linear algorithm. We have. I'm going to make sure different functions, right? It could be linear regression. It could be sigmoid, or maybe we're going to talk about it later. Consider this one, or maybe Bayesian. Consider this one as an equation or a function. But we are the machine try to find the parameter that built.
any guidance as to
Of course.
the domain?
Yeah. Of course. Yeah. No, not the MMB. The randomized. The MMB. Yeah. But in modeling, there's something called fine tuning. The fine tuning the model after the training. Yeah.
But before training,
Yeah.
it's just completely.
It's
Correct.
like, hey, it's up to you. Come up with
Yes.
whatever.
Yes.
But minimize loss.
Yes.
It starts completely random.
Yeah.
So is the idea to have the loss function equals 0? That would be
That's exactly. That's of course. Yes. If you can do that, of course.
So it just keeps going through the numbers.
Yes.
depending on what the
Yes.
loss is.
And try to adjust.
The
Yeah.
closer you get to 0 is what you
Correct.
want.
Yes. Yeah.
That is Skynet.
What is the one?
We're getting there.
This one.
No, one.
On the right.
This is constant. Any constant, right? Plus b. So b is the constant. I just multiply it to us to have like mx plus b, and it could be any constant, right? 2x, 2b, 3b. You know what I mean?
So that's the y-intercept, right?
And the y-intercept. Yeah, the y-intercept, for example.
But it's when
Consider as a matrix, b minus 1 is b. Instead, like consider as multiple multiple equations. So y1 plus minus mx1 plus b1, for example. You know what I mean? I'm just put it different way, in a matrix way, just to tell you maybe you have different features, age, size. You know what I mean?
Yeah, this
So,
line's amazing, actually.
yeah.
It's really good.
Yeah.
It makes sense.
Yeah.
So I noticed that B matrix is all one. It's constant one going all the way down.
Just yeah. That's what the question is. Yeah.
Okay.
Yeah. Why? Because I'm going to tell you it's y minus mx equal b. Like same equation, but multiple. Right. But could be maybe C, D, whatever. You know what I mean?
So L of M comma B, you want the M to be 0, comma B.
No, the function. So L is the function that depends on M and B. We need the answer. The L is equal 0.
The function depends on
The L is equal 0.
No, I want to see 0, comma B. Help me understand that.
Okay. So the idea is y, consider like in regression, right? So regression, we have a prediction, right? Prediction, y equal mx plus b, right? In order to have the fitted line, we need to y prediction minus y real equal to 0, right? So similarly, so this is the actual value. So this is for imagine this is for training, right? You have actual value, but when you get to the prediction minus actual, it should be 0. So consider this one as this is the machine was trying to do. The machine tried to do, you have the actual value and you have you have the few feature, and when you subtract them, you come up with a number using B and A that have 0. Then you come up with a model which is like a y hat, and use the y hat for prediction. Does that make sense? I can explain more into that one, but
Maybe the next slide.
yeah, maybe I will. Yeah, so I can explain more into that.
And that's why we
Yeah.
use, matrix multiplication for machine learning. That's why, right?
Yes, they use different techniques, matrices.
M is usually a very big matrix.
Yes, yeah.
Actually, sometimes not that big.
Only single value.
M? No.
No,
M is very big.
M, it could be multiple M, right?
Yeah.
It could be, don't fix on the linear equation. It could be, what's called, the third or second degree equation. Does that make sense?
Could be 1 million
Yeah.
by 1 million.
Yes.
That's common.
So let's not focus more into the math, but the whole idea is machine learning is the machine, you train the machine to come up with those parameters that help you to come with a model, use that model to predict. Forget about the math, okay? Okay, so look at linear regression, for example. I come up with this line. Now I have a model, this line, right? I use this data, I come up with this line, and then I can use that for prediction. This is for linear regression. But sometimes, not everything is linear, right? We have sometimes different function. We have this logistic regression is what we try to do with logistic regression is try to classify data based on probability. So they have a different function. It's called sigmoid function. It looks like this one. And the idea is you come up with values. If the value is less than the probability of 0.5, then you put in one class. If the value is higher than 0.5, it put in another class. So this is actually classify whether it is male or female, big size, rich or poor, whatever, based on probability. So if it is like 80%, that means it is mainly, category A versus B, right? So that's a different function. That's a different model, which is, we call it logistic regression. And actually, this is commonly used, logistic regression, to classify risky driver versus not risky driver, risky, patient versus not, yeah.
So when you're doing the learning, do you tell it in advance which model to use, or you tell it?
We're gonna discuss that later. Yes, but simple answer, yes. Depends on every problem situation. Okay, now we have it will classify a point based on your neighbor. So if this point, so you have let's say you have points, and those points, like those represent female, those represent male, and then you have points that new points come up, right? The whole idea is we maintain those points. It is not about coming with a model. It is not about. It's about having this data set, the training data set. And now a new point came, we try to figure out this new point falling within this group or that group, correct? So what it does, it will look at the nearest neighbor, and this neighbor could be any number, 1, 2, 3, 4, and this is called k. Isn't either k equal 1, k equal 2. If you are k equal 1, that means look at the first closest 1, k equal 5, closest 5. So here, closest 5, right? And then look at those 5. What are the majority? Here, the majority, for example, are male. So that means this point is going to be belong to male group. Does that make sense? So it will depends on the majority.
It doesn't make sense though. I mean, like,
Yeah.
even if in this room most people are male, if someone walks in,
If it's close.
if
No, 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 no.
that can be a female too.
No, 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 no. I'm talking about, okay, that's a good question. Okay. So it depends if you have data consists of male or female. And then you have a new point that either male or female. How do you classify that? Talk about classification. I'm not talking about unsupervised classification. I have two classes, and there is one point I need to either group into this class, or I know it is either male or female, but I don't know which one. So it looks at the nearest 5 or nearest number, k number, and if the majority of those nearest are certain group, then I will assign this new into that group.
For example, I'm here because
Yeah.
all 5 are me.
Yeah.
Guys, help me understand
Yeah.
what's purple. So I see the 3 blue dots inside the circle. I'm happy with the top blue. I'm
Yeah.
happy with the
I will
second blue.
explain. Yeah. Yeah.
And I want to know why this blue is not purple.
Got it. Okay.
It's,
Okay. Let me explain this slowly. Okay. So you have a training data set, right? I use that for prediction. The training consists of female, which is purple,
Purple.
male, which are males, which is blue or pink, right? And now I come with the new number. This is a new point. This is a new point. We don't know whether it's a male or female. Yes. We need to classify this new point either male or female. How we do that? We will draw a circle of that close to the k. Here k is 5. If it is 9, we draw a circle that combines the 9s, the nearest 9, right? And then try to look at those within that circle. If those are majority are male, then it's going to be new point is going to be going to male. If the majority are female, the new point is going to go into female. Does that make sense? Yeah.
So I think that makes sense, but following what you said as an example, right? So that means if a female walks in and she sits here, we're gonna classify her as a male.
Yeah, it could be. Yes, that's true. It doesn't. So this is the algorithm. It doesn't. Right.
But it's a good example to understand. Perfect.
Yes.
That makes
Yeah.
sense.
That's true.
One question. So
Yeah.
the GPT transformer, it has a similar thing where
Words, and you try to figure out what are the similarity of this word. What is the closest words that combine this one and the context, and they come up with, and that's why when you lead it, it will try to go with you. You know what I mean? Sometimes you say you are wrong, he say yeah I'm wrong, even if he's not wrong. Okay.
I'm very confused, not about the white dot in the center
Mhm.
or the 5 dots inside the cluster around it. I'm confused with the bigger,
Circle.
outside the circle. Thinking
The outside is the data set, the data set that we use for modeling.
and
Yeah.
purple on this side.
Yeah, this is it could be any shape. I'm just give you an example. Don't fixate it on the exact shape. It's just an example.
They're not.
Yeah, it could be here. It could be here. Doesn't matter.
Something's not clicking.
Yeah, it's not clear because I make it like just together. It could be at the top. I give you an example. You know what I mean? Yeah. But okay, but when we classify, there is always we run into should we choose what number of k nearest we choose? Should we use like 1? If you use 1, that means it's gonna go grab the zigzag everyone the closest one, and then you're gonna have something called overfit, right? You're gonna have 2 noisy data. But if you at the same time if you use like k equal 11, it's gonna be generalized. It's gonna grab all left and right, male, female, and then you can account with a line that does not represent the data, does not represent the pattern, right? So we have to choose the right one, maybe K5. That's where it will help that classify and identify what classes are. So this is there's a way to do that. There is a way to find which one is the right one, right K. So that's part of going through the algorithm and finding what the best case to use for classification. Just in terms of speed, the idea is instead of having a line, I will have a margin or a white space between the groups, right? So I have a group of, let's say I need to classify animals, maybe animals that has long nose, right? And bigger feet, for example, those like elephant, maybe dogs at the same time. And we come up with an algorithm is not identify the line that classify them, it's identifying those margin, right? And this is the machine does it. How it does it? It will try to create lane, try an error, make a line or make a line, and then try to make a range between those groups, right? Adjust. And when they adjust, they create this margin, and then they just look at those vectors. We call them the vectors, and then the point that touch those vectors, we call them the support vector. The support vector. So then we can end up, we don't need to look at the other data set. We're looking at those support. That's why we call it support vector machine, right? Support vector. So we come up with those lines, those points that touch the line, and then we come up with a wide range, and we know if the new data come outside this side, for example, then this is maybe those are elephants, otherwise they are dogs. Okay, so this is called support vector machine, and sometimes it's easy for line. But what if, to your point, what if the pattern is, you cannot divide it as a line, right? It's like circular. How we do that? Now we create a new dimension, not 2 dimension. We create it into 3 dimensions, right? We look at the height, for example, and then maybe you see the classification is the higher objects are the higher feature at the top, and maybe the lower, and then you have a plane that divide those points together, and we call them kernel, right? Kernel, and this kernel doesn't need to be like shape. It could be 3-dimensional shape.
So it's
Orthogonal, yeah. Okay. We call it kernel trick, right? So this is another way to do it, and one of the famous one is the decision tree, and the decision tree is actually simple. Is actually ask a question for each feature and then try to divide it yes or no. For example, if we are looking for like who is the risky patient, it looks at like you see over 50, yes, smoker, yes, then he's high risk, no, low risk, no, low risk. So it will divide, right, the information. It's not only one feature, maybe multiple feature. And the whole point is this one, we call it the leaf. Those at the bottom, we call the leaf. Those need to have as much information as possible. They should have as much information, which is we call them the information gate, right? So this part, if it is accurate, it has all the information, then you have a very good model, right? And you don't want to have a lot of levels. You want to have small levels, right? At the same time, those levels are more represent what the actual question is. And we call it prunes. Huh?
Is this related to random forest?
This is the origin of random forest.
This is the origin.
Original forest. So now I'm going to speak about random forest. So now we start with decision tree, right? And then if we need to go to random forest, how we do that? So actually what we do is we create a different tree. So we create like a subset tree, classify in parallel. Another tree, another tree, another tree, and then try to see the majority of what those three that do better, and then we choose based on the majority of those, the vote. So maybe this model and this model has more accuracy, or those two, then we can just use the best of those three. So this is called bagging, right? Which is actually random forest.
Oh, this is random.
This is random
How
forest.
do you train it?
It's same, yeah. It's just the model itself is actually create multiple trees, the decision tree. So random forest is actually decision tree, but multiple decision tree in parallel. Run in parallel.
And each decision tree, how do you train that?
It's same. It's through the random forest. The random forest, yeah. It does that by itself. It put all your parameters as if like it's decision tree, but it create by itself, create those smaller decision tree, and then it will use the majority vote, decide what model represent the random forest. Yeah.
Forgive my ignorance. Each one of these trees is identical in terms of rules.
Yes.
Correct? You're just running them in parallel.
Identical. It's going to be trained differently. it will create its own parameters.
Ah, so each one is actually different.
Different.
Okay.
It will have different. And then if this is accurate and this is accurate, then maybe you can just use those two as the majority.
Okay.
Help me bring this down to a middle school.
Yeah.
Middle school, high school level. So subset 1 has a bit of dark blue, subset 2 has a different bit of dark blue, right?
Uh-huh.
So I'm just wondering, if I apply for a credit card at different banks, am I expecting them all to reject me because I have the same credit score? I'm expecting,
No.
I'm
So
expecting them to give me the same credit limit?
I give you example. Let's say,
context.
yes, context. Let's say I need someone, right? I have 10 people to train them, 10 students to train them to be smart, right? So to represent a competition. So out of the 10, there are 7, they did well. Then I will rely on those 7 to come and use them for a competition, for example, right? Similarly, I have 4 models. Train them, same as I trained the decision tree model. 2 of them are doing well, I will use those 2. Does that make sense? Use the majority of good performance out of those few models that this random forest model does it. So this is all under the hood. It is not like I don't build this one. I'm going to just run the random forest. It will create those 3 on parallel, and then I get the parameter and then come up with the result. Does that make sense? Similarly, instead of doing it in parallel, it can do it in sequentially. We call them boosting. So you do the decision tree 1. So this actually is called boosting, gradient boosting, or extreme boosting, XGB boosting. So it does the first one, and then you get a model, right? And then there's error, and then you use that and improve it, fine-tune it, and then you run it again, fine-tune it, and then you come up with the best. Exactly. You come up with the best model at the end. You know what I mean? It's called boosting.
For the random forest, for the 4 subsets, are they all different data or just one data?
It's all one data, but the model has different parameters. So you run it, adjusting and inserting, you get a different parameter.
They're all same data.
Same data, yeah. It's only you run one single You run single of code. Random forest, just train the model. Under the hood, it create those.
So going back to the formula you presented earlier,
Yeah.
you use a model like this to identify some of the variables that you're going to push through the formula for the inference? Is that how would you use
So this one is based on decision tree. This is only, so the formula is linear regression is for mathematical, right? This is decision tree. It's like yes or no, as I mentioned earlier. Based on this one.
I understand.
Mhm.
You use this to optimize the input to the other formula, like the variables you're looking for.
No, this is a different, this is a separate algorithm.
Okay.
So as I mentioned, machine learning has different learning algorithm.
I wasn't sure.
Yes, correct. Yeah. No.
That's something even
Yes, we use it at different criteria. Maybe there's the use case you try to model at, some use cases I have seen. You come up with like a model through decision tree, and then the result maybe use another model to use it. But generally speaking, every problem has its own machine learning algorithm.
So they're mutually exclusive.
Yes. Yes.
Okay.
Okay. All right. Almost there. So this is the most utilized, especially in computer vision, which is the neural network or deep learning, right? And this is actually what happens is you have like an input, and usually an image, and then it will, through different layer, it will grab, understand each feature from that image. Maybe like the edges, maybe the content inside, maybe the color. You divide them, and then you adjust them using another layer, and then until you come up with an abstract form, and based on the label data, it will tell this abstract is what the classification is. Whether it is a zebra, whether it is a horse, mainly computer vision. But this is right now most of the application is based on deep learning and based on this as I mentioned earlier on those image classifications based on deep learning. Okay, now almost there. The unsupervised learning, I'm going to just go quickly, which is the clustering algorithm, which is I have data set, I'm just cluster group them. Bigger size points, I'm going to group them into bigger size, smaller size, right? you know, certain characteristics, I'm gonna group them. We call it K-means. Maybe there is another one. It's called dimension reduction, which is I look at a feature and try to, if it is high division, I'm gonna just try to eliminate all the feature, make it abstract, and then based on this abstraction, I can decide whether it is a cat or a dog or whatever. Instead of high dimension or